Embedded operating systems, design principles for resource-constrained environments. This presentation provides an overview of embedded operating systems, which are crucial for devices operating in environments with limited resources. What are embedded operating systems? They are specialized operating systems designed to operate within the constraints of limited processing power, restricted memory availability, power consumption constraints, real-time requirements, and specific hardware integration. Common applications include smartwatches, smart home devices, automotive systems, medical devices, industrial controllers, and Internet of Things sensors. Key characteristics of embedded operating systems. First, resource efficiency. These operating systems are optimized for minimal memory footprint, central processing unit usage, and power consumption. They often use specialized memory management techniques. Second, real-time capabilities. They provide deterministic response times with guaranteed deadlines, critical for systems where timing is essential, such as medical devices and automotive systems. Third, reliability. They are designed for continuous operation without failure, often including fault tolerance mechanisms and watchdog timers. Fourth, hardware specificity. They are tightly coupled with specific hardware, often including custom drivers and direct hardware access for efficiency. Fifth, modularity. They feature a component-based design, allowing the inclusion of only necessary features to reduce footprint and resource requirements. Sixth, long life cycle. They are designed for extended deployment periods, often requiring robust update mechanisms and long-term support. Memory management in embedded operating systems involves several techniques tailored for resource-constrained environments. First, static memory allocation. All memory is allocated at compile time with no dynamic allocation during runtime. This provides predictable memory usage but less flexibility. Second, memory pools. Pre-allocated blocks of fixed sizes eliminate fragmentation and provide deterministic allocation times. Third, memory protection. Hardware-based isolation between processes prevents memory corruption and improves system reliability. Here are some examples of memory pool implementation and static allocation in embedded operating systems. Real-time scheduling in embedded operating systems. Several algorithms are used to manage tasks in real time. First, rate monotonic scheduling, abbreviated as RMS. This involves static priority assignment based on task periods, giving higher priority to tasks with shorter periods, and is optimal for periodic tasks with deadlines equal to periods. Second, earliest deadline first, abbreviated as EDF. This uses dynamic priority assignment based on absolute deadlines, where the task with the earliest deadline gets the highest priority and can achieve 100% central processing unit utilization. Third, fixed priority preemptive. Tasks are assigned static priorities, and higher priority tasks can interrupt lower priority ones, offering predictability but potentially causing priority inversion. Below is a priority-based scheduling visualization. Power management in embedded operating systems. First, sleep modes. Multiple power states with varying levels of component shutdown, balancing power savings with wake-up time. Second, dynamic voltage and frequency scaling. Adjust central processing unit voltage and clock speed based on workload, achieving significant power savings during low-demand periods. Third, peripheral power gating. Selectively powers down unused hardware components, reducing static power consumption of idle peripherals. Here is an example of power management implementation in embedded operating systems. Popular embedded operating systems include Free Real-Time Operating System, abbreviated as FreeRTOS, a market-leading real-time operating system for microcontrollers and small microprocessors, designed for reliability and ease of use. Zephyr Real-Time Operating System, abbreviated as ZephyrRTOS, a scalable, security-focused real-time operating system for resource-constrained devices, backed by the Linux Foundation. VxWorks, a commercial real-time operating system used in critical systems including Mars rovers, aircraft, and medical devices. Embedded Linux, a full-featured operating system for more powerful embedded systems, highly customizable with extensive driver support. Mbed Operating System, abbreviated as MbedOS, an open-source operating system for Internet of Things devices based on ARM microcontrollers, focusing on connectivity and security. Riot Operating System, abbreviated as RTOS, the friendly operating system for the Internet of Things, designed for low-power devices with minimal resources. Design challenges in embedded operating systems. First, resource constraints. Limited memory, processing power, and energy availability restrict operating system capabilities and design choices. The approach is modular architecture, allowing inclusion of only necessary components, along with optimized algorithms for minimal resource usage. Second, real-time requirements. The need for deterministic behavior and guaranteed response times for critical operations. The approach involves specialized scheduling algorithms, interrupt handling, and priority-based execution models. Third, security concerns. Embedded systems often control critical infrastructure and handle sensitive data with limited security resources. The approach includes secure boot, memory protection, encrypted storage, and minimal attack surface design. Fourth, long lifecycle management. Embedded systems often remain in service for decades, requiring long-term support and updates. The approach includes modular update mechanisms, backward compatibility, and robust fail-safe systems. Future trends in embedded operating systems. First, artificial intelligence integration. Embedded operating systems will increasingly incorporate lightweight artificial intelligence frameworks for edge computing, enabling local processing of sensor data, reducing latency and bandwidth requirements while improving privacy. Second, zero-trust security. As Internet of Things devices become more prevalent, embedded operating systems will adopt zero-trust security models with continuous authentication, secure enclaves, and hardware-based security features to protect against sophisticated attacks. Third, energy harvesting. Future embedded operating systems will optimize for ultra-low power consumption and incorporate advanced power management for energy harvesting applications, enabling perpetual operation without battery replacement. Fourth, over-the-air updates. Secure, atomic over-the-air update mechanisms will become standard, with sophisticated rollback protection and minimal downtime, extending device lifespans and improving security posture. Fifth, mesh networking. Embedded operating systems will incorporate advanced mesh networking capabilities, enabling devices to form self-healing networks with dynamic routing and improved resilience against connectivity failures. Sixth, hardware abstraction. More sophisticated hardware abstraction layers will emerge, allowing applications to be portable across diverse hardware platforms while still maintaining access to specialized hardware features. Embedded operating systems will continue to evolve, balancing resource efficiency with increasing functionality demands while maintaining their core characteristics of reliability and determinism. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.